Okay, class, we're now to nerve tissue 2. Nerve tissue 2 in my website. Nerve tissue 2 in my ENP1 website. Now, this particular PowerPoint here, I'm not going to have a lot to say about it, because if you studied in detail my electrophysiology module, both the handout and the PowerPoints and the video and everything, then really there's not a lot to say on this one, because this is basically, so we're just going to kind of walk through real quick and get to a couple of things, and that's about all in this one. All right. We talked about neuron function. Okay. Electricity, I talked about in the electrophysiology. Definitions of voltage, talked about that. So you can look at this one, but you can do this one on your own. It's really nothing different. Gated channels, talked about those. This here, all of this. Everything in this particular aspect was basically talked about. So there's really not anything to really discuss of any nature in this particular PowerPoint section. We'll go a little further. We talked about this, the voltage, intracellular fluid, extracellular, resting membrane potential. So this one you can just kind of review through, but you should be able to understand everything very well. Two graded potentials, action potentials, depolarization, all of this particular material here. Hyperpolarization, graded potentials, depolarization waves, everything was in the electrophysiology. So if you did that and then you looked at this, I think you should be able just to master this quick. Resting state, properties of gated channels, that, depolarization phase, repolarization, hyperpolarization, this here, talked about that, repolarization, propagation of action potential, conductivity, other words, talked about all of this particular material here, threshold, this here. Now I'm going to say something on this slide here, right here. Okay. Now, remember that action potentials are all or none. All or none. They only reach a certain height. They're all or none. So what I want to use this for is not what it's really being used for in a way, but I want to use it in this case. How do you code intensity? Okay, now let's think what I'm saying here. How do you code intensity? All right, let's use an example. If you put your finger on an iron and it's a little hot, and then you turn and the temperature went up a little bit, it got hotter and hotter, how would the brain interpret that? How would you even send the signal to the brain? Okay, since action potentials cannot get any higher, then you can't say, well, the hotter it gets, I'm going to send bigger action potentials to the brain so the brain will know it's getting hotter. That's not going to work, because action potentials are what? All or none. So the way to code intensity in the sensory, let me say this again, the way to code intensity in the sensory to let the brain know that things are getting worse, hotter or whatever, is frequency of firing of the action potentials. So what would happen is, if we had what we call an oscilloscope, it's a little device that you could hook and see how fast the action potentials, or the other devices too. This is how the thing would go if I did it sound-wise. So the iron is hot. You're getting some action potentials through the sensory nerves going to the brain. They're firing. Then you turn it up. They get faster. Then they get faster than that as you turn it up. So all intensity, or if somebody's standing, you get somebody standing on your finger, you didn't know it, and then some kind of way they're pushing down harder because they didn't realize they're on your finger, how would that increase in pressure be interpreted by the brain? Frequency of firing of action potentials. So in all changes in intensity, the frequency of firing, a slower rate would go to a faster rate. That's how it's determined because, again, action potentials cannot get any higher. So I'm using that in this case. The stronger the stimulus, see how that stimulus is here versus that one? The stronger the stimulus, the faster the firing rate. Okay? All right. So that's one little thing to say. Okay, we know about absolute refractory. That's in the electrophias. That's in the electrophias, relative refractory. Conduction velocity is there too, but I'm going to bring that up here. Okay. Some neurons are faster than others. Some neurons are what? Faster than others. Now let me kind of explain that to you. Okay. Let's theoretically say that you're going to mail a letter. And you decide to go and pay that $10 or whatever to do an overnight mailing of your letter. But the guy the person that gets it is not going to even look at it for a week. What's the use of paying that $10, let's theoretically say, if the person's not going to look at it for a week? Why not just let it go regular mail? Because that's the way that they're going to do it. So what's my point? Anything that needs to arrive, to travel fast, needs fast neurons. Things that don't need to travel fast do. Like, for example, if you're getting burned, then you want fast neurons. Okay? But if you're having a change in intensity, let's say of pressing on your two fingers together, you don't need it that fast. Now, where it really comes in is this. Remember we talked about the autonomic nervous system and the somatic. The somatic nervous system, which would be like remember I said on somatic sensory, it'd be like the skin, for example. We'll just use that. If you get scratched or something getting on your skin, you need to know right away. So that somatic sensory needs to go fast. But if there's some change in the filling of your bladder, which is autonomic sensory, so that's an organ, it's not that critical. You don't need it that fast. What you going to do about it? Nothing differently. So therefore, if you need something fast, you use fast neurons. If you don't, you don't. Now, the faster the neuron, the more ATP you're going to use. See, that's where like the money thing with the mailing of the letter. All right, so that sets the stage. But now, what is the key factor in the difference in neurons as far as conduction speed? The larger the axon diameter, the faster the travel. Okay, they have less resistance. Myelination. So the axon diameter and whether you have myelin or not makes the difference. So if an axon is big and it has myelin, that's the fastest you get. And then it progresses down from there. Okay? What the myelin sheath does is speeds it up. Now we're going to look at this. Now this is something all right. Now what I want you to know on this here is this. First of all, I'm going to go back here and pick up a myelinated neuron. If I can find something here. Okay, let me find a neuron. Okay, over here. All right, that's a myelinated neuron. All right, the type of conduction done in a myelinated neuron is called saltatory conduction. The type of conduction is called saltatory. S-A-L-T-A-T-O-R-Y, saltatory. See if I have it here. No, I don't. So it's called saltatory conduction. Okay, I'm going to, matter of fact, insert it here so you can see what I'm speaking of. Okay. And so on this saltatory conduction, we'll do this if I can. A little trouble getting this to work, okay? Saltatory. Is a jumping conduction. A jumping conduction. Okay, this is how it goes. The action potential comes down. Since the myelin covers up the voltage dependent gates, you can't do the action potential on the membrane because the gates are closed, because they're covered up by this plug of fat, this lipid. So when the action potential comes down, it has to stop here. Now as the action potential comes down, don't forget that you're creating a charge. See, out here is extracellular fluid, in here is intracellular fluid. So the charge on the membrane is also going off into, because a charge creates a charge field. So it's also going off into the extracellular fluid and the intracellular fluid. The charge is here moving, but it's going here also. Here is an active spread. Remember we talked about the coat hanger that I mentioned before and the firecracker fuse. So here is active. When it goes into the fluids, it's passive. It is going fast, but it's passive. Okay? Now when it goes and it loses stimulus ability because of the fact it loses the power, shall we say. But then, if there's still enough power when it's going here, going in all directions in these fluids, to come here, because it'll hit here too, and what? Have enough power still to reach threshold, then you would start again on the membrane. Then it would again have to stop, but it would send out the charge field, and then again. Now let me kind of explain. Let's use football for example. Let's say Usain Bolt, who happens to be the fastest running human, I think, right now. I think somebody else beat him recently. Let's say he starts and a quarterback start. They both on a football field. Usain Bolt takes off running. The quarterback throws the football to a person. Now, even as fast as Usain Bolt is, he's not going to beat the football getting to the next person. And then the next person throws it to the next person. Now, Usain is fast, but he can't do it. As long as that football is going in the air, it's going faster. The difference is Usain can keep running the entire football field. The quarterback can't throw it to the rest of the field starting at the 0-yard line. So the football is doing a passive spread because wind resistance and everything is slowing it down. But when the next guy gets it, he can start it again. But if it was just the quarterback and Usain, and the quarterback threw the football, the initial part, yes, would beat Usain Bolt. But if there's nobody else to pick it up, Bolt's going to make it all the way to the end because he's doing an active run where the football is doing a passive. So let me apply it one more time. When this comes here, it goes off into the fluids because charge will move into these electrolyte latent fluids. Remember, it got sodium, potassium, all kind of stuff. But it loses it because it's a passive spread, just like we did with the coat hanger. Just like we did with the coat hanger in that example. And then all of a sudden, though, if this plug is not too long, by the time it gets here, it still has not lost enough charge to create another action potential there. Thus, the action potentials are jumping, saltatory. They're jumping from one to the other to the other. That speeds it up. That's why the plugs could not be one solid plug, because then you wouldn't have enough oomph to get to the end. That's why it has to jump, and a plug here and jump and jump. Please look up saltatory conduction. It's a jumping conduction. I've tried to give you kind of an explanation of how that occurs best I can. Thank you.